All right, so it's 3 minutes after, and we have our speaker Jørgen, and he has his title up, which
Yes.
which you can all read. And I think Jørgen, whenever you're ready. So
Yes, and that I am. So yeah, thanks for the invitation to give a talk, or actually to give two talks. That's very generous. Right, so the title here is K-theoretic sheaf counting invariants of Quot schemes on C4. And you know, you always write the title before you write the talk. So I should say, first of all, mostly really this talk will be doing Hilbert schemes on C4, because the added technicality of doing Quot schemes is not really, I don't know, it doesn't really help explain the point all that much, but just so we'll mostly stick to Hilbert schemes. But so the things I say, there's a version that works for Quot schemes as well. So what this is about is, well, it's essentially it's essentially a computation of these K-theoretic sheaf counting invariants, which are only quite recently been defined, at least in a sort of proper geometric way. And so the main goal is to explain what these are and to explain a theorem which gives a surprisingly simple closed formula for the computation, which was conjectured by Nekrasov. So yeah, I mean, those are basically the two goals of this. So to explain this thing, I decided it's useful to start by setting 4 equal to 3 and really do the same story for Hilbert schemes of endpoints on C3. Right, so the moduli scheme of closed subschemes of dimension 0 and length. So really generically endpoints, and then they come together to form some non-reduced subscheme in various ways, but mostly it's just the moduli scheme of endpoints on C3. So, and I wanna talk about how you understand the K-theoretic Donaldson-Thompson variants of these. So, so the reason I want to discuss this first is, well, one is sort of as a matter of logic, the computation we do at a certain point reduces to exactly the same reduces to the computation of these Donaldson-Thompson variants for Hilbert C3. So, you know, at least I should say what we know about these things. But secondly, and maybe more importantly, the formal setup for defining and for analyzing these sheaf counting invariants on C4 is extremely similar, like surprisingly to me, similar to what goes on in 3 dimensions. And since the 3-dimensional setup is somewhat more straightforward, I think it's sort of useful to give that simpler story first. So so we want to study these MNs, these Hilbert schemes of endpoints, and the sort of so that's a certain scheme, and a key geometric part of the setup is you have a 3-dimensional torus, which, well, first of all, it naturally acts just by scaling the coordinates of C3. And then since Mn is a modular space of objects on C3, T also acts on Mn. And so to get going with defining Donaldson-Thomas invariants, technically the first thing you do is to observe that Mn has a perfect obstruction theory. I should say, maybe this goes without saying, but please do ask questions. Of course, it's hard for me to know exactly how to pitch this. So any feedback on where I'm at is good. And also, this is only the second time I give a talk about this. So anything to help me polish it is useful. Anyway, so Mn has a perfect obstruction theory, which it's not super important what that is technically, or the full rigorous definition isn't important for us. But the main data of this is we specify at each point. So at a point Z in Mn. So here Z, is a closed subscheme of C3. There we have, the tangent space, which is isomorphic to x1 OZ OZ. And then we have the obstruction space. So the obstruction space and just to have said this in words, I mean this is meant to capture the fact that locally near Z, you have the tangent directions, and the scheme Mn is, you can think of as being defined by equations which are where the equations are labeled by, well, not the obstruction space, but it's dual. But anyway, roughly speaking, you've got x1 many tangent directions and x2 many equations. So from this, you compute the virtual dimension, being the dimension of the tangent space minus the dimension of the obstruction space. And in this case, this happens to be 0, which since Serre duality tells you that actually x1 and x2 have the same dimension in this case. Okay, so this is just sort of okay. So this is, I mean, the main point is that this dimension of tangent space minus dimension of obstructions is constant. That isn't technically the definition of having a perfect obstruction theory, but it's sort of it's the main thing. It's the main thing you need. It's the main thing you should hope for in order to define a perfect obstruction theory. Okay, so what you do once you have this? Well, this is you can then apply some mid-90s technology to say that we can then define the virtual fundamental class so some class living in H0, T equivariant, because T acts on everything of Mn, and classical Donaldson-Thomas invariants, or sort of the first iteration of Donaldson-Thomas invariants, is trying to compute this thing, compute this class. So that's not going to be really what we're interested in here. We can also define the thing we're interested in is the virtual structure sheaf, which, despite its name, is not a sheaf. So this is a K-theory class. So this lives in the T-equivalent K-theory of Mn. Right. So this is some. I mean, it's not super important. Well, it turns out not to be very useful actually in practice unless you're working on theoretical foundations to know exactly how you get from what a perfect abstraction theory is and how you get to define these things. But we'll see in a while how you compute them. And you know, I assume this you might have seen these things in the seminar before. So I learned most of it from reading Andre's notes. So anyway, so the thing the K-theoretic DT invariant alluded to here is then computing taking the Euler characteristic of this over, or more generally, you can take this is sort of the first thing you can do, but you can also try and compute more general things, tensoring with f, where f is some locally free K-theory class. So f is, I mean, maybe just take f to be some locally free sheaf. Again, you've defined the K-theory class, and computing its Euler characteristic is well, it's at least a problem. Whether it's an interesting problem depends on what you choose to insert, perhaps. Okay, so I should specify what I mean when I say this Euler characteristic. So if you haven't seen this before, you should object that this doesn't really make sense. So I shouldn't be able to take the Euler characteristic of something living on Mn, because Mn is not compact. The way we define this, so Mn is non-compact, and so what we have to do is we define this chi operation via T localization. Okay, so abstractly, what does this do? It's just a general just a general recipe where you can well, it's basically since the T fixed locus is compact, and I'll say a little bit more about this shortly. Since this a T fixed locus is compact, there's just a general technique for applying in any setting for once you have a T equivariant K-theory class for defining this this chi operation or the Euler characteristic. So we define this thing so it's not going to be an alternating sum of cohomology spaces. It's not going to be defined in that way, but it's going to be some element living in K naught T of a point, but in some localized version of this. Okay, so to be concrete and explicit here, so K naught T of a point, that's explicitly the polynomial ring in positive and negative powers of the Ti, where Ti are the coordinates of our torus. Right, and this thing then localizing means, well, you have to add inverses to some elements, and that's just, it doesn't really matter for us how many well, we just make life easy for ourselves and just invert everything in sight. So we're after computing an element in. So the upshot is defining this via localization means the output of the computation, applying chi to this virtual structure sheaf should give you a rational function in 3 variables, right? So you know, suppressing all the technical stuff about perfect obstruction theories and how to define everything. The upshot is, in the end, we can apply this procedure and get a rational function, which we'd like to compute. Okay. So, but more than this is true. You know, so not only does localization allow us to define this thing, it also gives us the best way to, well, it gives you a way to compute this thing. So specifically, we can describe explicitly what the fixed points here are. So you know, Mn we can think of as the ideals contained in the polynomial ring in 3 variables, and such that the quotient as a C vector space is n-dimensional, and then the fixed point locus here. So an ideal which is fixed under all rescaling of all parameters, that's the same thing as a monomial ideal. So generated by monomials. Such that, well, the same thing holds. And these things are explicitly describable by, these are in bijection with a set of plane partitions. Plane partitions, which so if I could draw, what you should picture is, you know, boxes stacked neatly in the corner of a room. That's a visual representation of a plane partition. Boxes stacked neatly in the corner of a room, such that you can't push them further into the corner. Any such configuration, that's a plane partition. So plane partitions of n. But to be just to give the formal definition, it's a subset of the positive orthant in the integer 3D lattice and of size equal to n. And let me just write down this. This is so the complement should be closed under adding on things in the positive orthant, right? So this thing should be contained in. So again, I mean, it's not terribly important for us. Oh, did I?
Yeah, Jørgen, I think we're not seeing what you write after you.
Yeah, exactly.
Partitions of n.
Exactly. Yeah, I saw the screen change here. So let me just see. Can I again? I assume you were all just taking notes exactly as I.
Okay, now
writing down my every word. Yeah. No. Yeah. Right. Okay. Yes, it's back. Right. Okay. So it's not. I mean, again, working with this stuff, of course, you have to know what this is. For our purposes, it isn't really. I mean, if you're seeing this for the first time, I don't mean to say that I didn't. I mean, yeah, it's not. the main point here is that the fixed points are, we know what they are. We can sit down and describe them. They're completely explicit. I mean, they're combinatorially explicitly defined objects, so we know what the fixed points are. That's the main takeaway, and they're defined in terms of very combinatorial objects. And moreover, like as a particular consequence of this thing, of this description, like a substatement here is that this thing is zero-dimensional. It's a collection of finitely many points. Okay. So then there are general techniques telling you how to compute these K-theoretic, a general theorem, the virtual localization formula due to Chican, Fontanini, and Kapranov. Which tells you that this thing that we're eager to compute is going to be a sum over fixed points.
I apologize. I think it's again stuck at the zero-dimensional.
Oh yes, it is stuck. Yes. Okay, let me try. So I don't know. I don't know what the. Let me see. So what I can try to do is I can try and log on with this iPad. That's a second unit. Oh yeah, now it's slowly catching up. Okay, so let me try and log on using this. Log on using this iPad and stream it directly from the iPad, because this. Sorry, 1 second. Okay. That. Oh.
If it doesn't work, no problem. We can. Well, you were doing great, I think. And there's some slight delay occasionally. That's okay, I think.
Yeah. No, I'm.
Feedback is worse. Yeah.
I can't really ask the question without causing a massive. So what I want. Yes, I think I did it. Yes, I think I fixed this now. Okay, I'm close to fixing this, I think. I'm going to share the screen, and
Oh, great.
Okay.
We can see the screen. Yeah.
Yes.
And we can hear you. Yeah.
Yeah. Perfect. yeah, I don't know. I guess everyone, we've all had like some experience with fixing these kinds of things in yeah. Anyway, okay. So back to the mathematics. We have now the yes. Okay. So we have a virtual localization formula, which I was about to write down, which is so we want to compute this virtual structure sheaf. And what is the computation? The computation is going to be a sum over fixed points inside this Mn, where again recall this thing is a closed subscheme of C3, and what is the contribution of each fixed point? I'll just write it down and I'll explain the notation after. So right, so it's okay, so it's this fraction, and how do we interpret this fraction? Well, first of all, when I write this wedge bullet of something, I mean this is slightly dodgy notation, but what I mean by this is, I mean the alternating sum of wedge I alphas. So I mean where alpha is some K-theory class. Right, and how do I want to think about these things? Well, the elements here are they're going to be so the elements here are T representations. So the T representations, and I want to think about them as polynomials in the Ti, the parameters of the torus. So your own polynomials in the parameters of the torus. And so the upshot is, so I take some polynomial, I do this, I take this polynomial, I apply this operation to it, and I get this fraction. So this fraction now in the end is going to be an element, it's going to be some rational function. Okay, so just to have so and you can maybe from this you can maybe guess at what the general statement is. So at the beginning of the talk I told you like this is the tangents, and this was the obstructions, and this is in the general case, at least for isolated fixed points, this is giving you the shape of the general virtual localization formula. You put the obstructions on top and the tangent space in the the obstruction in the numerator and the tangent space in the denominator. Okay, and just to have sort of completely pinned down this, so we know we're on the same we're on the same page here. In the case where n equals 1, there's a single fixed point, so just the point at the origin, in which case you compute that x1, the x1 space is t1 plus t2 plus t3, and x2 is t1 t2 plus t1 t3 plus t2 t3, and then we get a full and complete computation of a dt invariant, which is then 1 minus, well, it is what I write down. Right. Okay. So this is meant to illustrate. Well, okay. So in general, we have complete combinatorial control, at least, over what the fixed points are, and these T representations are also concretely computable from the combinatorial data specifying Z. So so if you have a sufficiently powerful computer and enough time, you can compute this for any n. There's like some from one perspective, once you have this formula, the problem of computing VT invariants, K-theoretic VT invariants for Hilbert it's essentially solved, right? You just this is what it is. Now of course, so from another perspective, you don't necessarily understand the answer, right? Because you're summing over very many fixed points, and you're adding together rational functions which are apparently unrelated to one another and pretty complicated. So as we'll see, the answer when you do this huge sum turns out to have an extremely simple form. But in order to prove that it has an extremely simple form, you have to do something a little more subtle, and you really have to understand this object, this virtual structure sheaf, in a more global way, in a more sort of it might be a stretch to call it a geometric way, but more than a computational way, at least.
Maybe not this particular sum, right? I mean, this particular sum probably is not going to be so nice because
that's true. That's true.
Yeah.
That's a good point. Good point. So this sum, even if you understand this particular sum, even if you understand over well, which we will in a second, it won't reduce to something nice. But yeah, you're right. Okay, with that caveat, which will show up later, a closely related sum will have a nice answer. Okay, so the main well, okay, so the sort of key, so the main sort of geometric input we need here is we want to write Mn as a critical locus. Okay, so in general, there are many different kinds of Donaldson-Thomas invariants. Like there's there's a whole long list of various adjectives you can put in front of Donaldson-Thomas invariants and get different things. But if you sort of restrict to saying as well that Donaldson-Thomas invariants are about defining counts of sheaves on threefolds, then the threefold may be Fano or it may be Calabi-Yau, and the Calabi-Yau case and the Fano case behave quite differently. But if you're dealing with counting sheaves on a Calabi-Yau threefold, the thing that's sort of technically at the heart of many of the tools you use and many of the sort of, well, it's at the heart of much of the technology you use in order to compute these, is the observation that in general, let me just say this imprecisely. So if M is a modular space of sheaves on a Calabi-Yau threefold, then locally M is a critical locus, meaning it sits inside something smooth, and it's defined by the vanishing of the partial differentials of some function. Okay, so there are general theorems proving that this happens in a large amount of generality. We won't need those theorems because we're trying to understand Mn, where we're extremely lucky, and because Mn is actually, we can remove the adjective locally, Mn is actually just on the nose, globally a critical locus. So how do we see this? Well, this is the construction where, okay, so you start up with Mn is Hilbert C3, and this is, okay, so here the useful description of Mn is a set of surjections from the polynomial ring in 3 variables to n, where n is a module over this polynomial ring, and its dimension is n. Okay, so to write Mn as a critical locus, we need to embed it in some ambient space, and this ambient space will be the non-commutative, what we call the non-commutative Hilbert scheme. Which is exactly the same thing, except now you take the instead of the polynomial ring in 3 variables, you take the polynomial ring in 3 non-commuting variables. So here are modules over this. Modules, well, I guess left modules or something. Okay, yeah. And again, dimension. Okay, so it's kind of straightforward to see that there is an inclusion here, right? A module over over non-commutative, sorry, of the polynomial ring. I mean, the data on the right-hand side here is something which happens to lie in this smaller subset if the elements x1, x2, and x3 happen to commute when they act on n. So basically, I mean, if you have something here, you can map it to something here. It's easy to see on points, but it's also easy if you define the scheme structure on all of these things. It's easy to write down the map. Okay, so this NC help is woof. Right, this NC Hilb is a so Hilbert scheme of endpoints on C3 is a famously horrible object from a geometric perspective. It's got I don't think we really know its dimension in well, at least not for arbitrary n. It's certainly like both non-reduced and not irreducible, and has like horrible singularities, and you probably shouldn't even try to understand it geometrically. On the other hand, the non-commutative Hilbert scheme is as nice as can be as a geometric object. So this thing is, well, and the way you see it's nice is you can describe it as a quotient of as a GIT quotient. So you take a linear space where the first factor is telling you where you send the unity inside n. The last 3 factors are telling you how x1, x2, and x3 act. And then there's no more data to specify. So that's the full thing. And then you need to take some open subset in here in order to ensure surjectivity. But anyway, the point is that this thing, if you write it as a quotient in this way, that's how you see that it's smooth and of dimension 2n squared plus n. Okay, so this is a nice smooth ambient space, and now if we define w, we define the function w from NC help to C. We can define it at a point. So a point is some surjection, and what do we define it to be? We take the trace of a certain so here, I mean, so you write down this non-commutative polynomial. This non-commutative polynomial you think of as an element of n, so this is something you can take the trace of. And then the claim is that this thing, that the Hilbert scheme now is the critical locus of this function, right? So the vanishing locus of the partial differentials of W. Okay, so this is right. So if you haven't seen this before, and if you're sort of still on board with what we're doing here, like the geometric setup, then I strongly recommend proving this claim, because I don't know, I think it's like a good joke or something to see that when you try and compute the partial differentials of this guy here, the partial differentials of W, you see that what falls out immediately is the condition that these operators x1, x2, and x3 actually commute. So it's a very simple thing, but it's a fun thing to do once. Okay, so now we have this. What do we use it for? Well, we use it for now giving an explicit description of the virtual structure sheaf. So the virtual structure sheaf, so one way to motivate it by some loose analogy is to say that your modular space is cut out by, you expect your modular space to be, I mean, you pretend your modular space is cut out by a section of some vector bundle on the smooth ambient space, and then you write down. So this section it's not necessarily transverse, but if it were transverse, you can compute the structure sheaf of the modular space by taking the Kool resolution. So the thing to do the virtual structure sheaf is saying, just take the Kool resolution. And here, this extremely nice situation does happen. Mn is cut out by a global section. So Mn is cut out by a section of a vector bundle on this smooth ambient space. I mean, it's cut out by a section of the cotangent bundle on the ambient space. So we can actually do this. So let me do this in stages. So let me just first write down the complex here, which is so write down the Kool complex associated with this one form. So this is a section of omega-1 NC help, and then write down the associated Kool complex, and this ends with right. So this is some complex of sheaves on NC help. Okay, so it's a complex of sheaves on NC help. It has the nice property that if you take its cohomology sheaves, so this thing, just take the cohomology, this thing is this is a graded, I mean, the cohomological degree gives you a grading. This is a graded sheaf, and it happens to, I mean, it's supported on the Hilbert scheme, so it actually lives where you on the scheme you care about. And then the statement is that over Mn is the class of this thing. So there's some sort of categorification, decategorification ladder here, where this thing C is somehow what the universe gives you, and because we want something, because we want to in the end compute something, we first take the cohomology of that to get something which lives on Mn, and then we further reduce that by taking the associated K-theory class. but somehow this intermediate stage is technically very useful to have something which is better than a K-theoretic class, but which forgets the which I mean, it has the advantage of actually living on M and living on the Hilbert scheme. Anyway, this is I mean, this is set up for a parallel story which will happen later in the 4D case. So this is something we should aim for in the 4D case. Okay, so the final thing I want to say about this 3D story is the result, is the computational result that we're going to use. And so to state this, we introduce some notation, and this is so this is here is the Andre's point, his mark previously is we actually don't want to compute. Well, okay, we might try, but if we want to have a good answer, we don't want to compute over directly. We want to compute some variant of that. So this thing is it's over. So the virtual structure sheaf, we're going to twist it by K and C Hilb, or if you like, if you want to be sort of another way to write this, which works more generally, is to call this thing square root of K ber. So this is the symmetrized virtual structure sheaf. Anyway, that's just a new class, which I don't have a very simple explanation for why you consider that thing, but it is the thing that gives you which gives you the yeah.
If I may, it's no, that has a good explanation, because it's like the I mean, this is why Nekrasov considered it in the first place, because this is like the index of Dirac operators as opposed to the index of the Debar operator. So that's for people in kind of classical K-theoretic training, that's a very natural thing to consider. It's like the
yes,
yeah,
yes, yeah. I've seen, I've heard, I've read that phrase before, but I don't have the required classical K-theory training to to find that
right. But some people in our seminar do, and so like
okay,
Igor, for example, proved theorems about these things for like many years ago.
Good,
so,
good.
Yeah,
okay,
yeah.
thanks. That's good. For me, I can maybe say one thing I find kind of appealing is, just by looking at looking at this expression for it, tensoring with K and C Hilb makes it look. I mean, if you examine what happens to this complex, you end up seeing, instead of wedge powers of T, you see wedge powers of omega, which is I don't know. It looks like looks similar to a Dirac complex, which you might expect that to have other properties. I'm not sure if that's
yeah, I totally agree with that. That's one. That's another way to say it. Yeah.
Yeah.
You certainly, if you wanna, if you want to compute cohomology of some sheaf you don't know anything about, it's much better if it looks like a Dirac cohomology rather than a cohomology of polar vector fields. So.
Right. So I mean, I'm not saying yeah, okay. So I'm not really saying from that I would be able to predict that the end result would be more computable, but anyway, it's not completely a priori unmotivated. Anyway, during this discussion, I've introduced more notation, which is just this very simple thing. If I write something and I take square brackets around it, I mean alpha, just the sum of the square root of it minus the sum of the inverse square root of it. Anyway, that's just to save some electronic ink. And the final thing is the following definition. If f is a function of z1 up to zr, then the platistic exponential Then the statistic exponential is defined to be the exponential of the sum of the, well, it's this expression. Let me just write down the expression. Okay, and we assume, so our function is probably going to be given to us as a formal power series, and if you sort of, you put some condition on this power series to ensure that actually this expression on the right-hand side makes sense, right? So there are expressions for which this does make sense, sort of formally algebraically. There are expressions for which it doesn't make sense, but we will just sort of always be in the case where it does make sense. And to motivate this, it's roughly speaking, if f is the character of something, then this operation corresponds to taking the the free the free symmetric algebra on what you have, or just like the sum of all the symmetric powers. So that operation, doing that operation on representations, corresponds to taking the statistic exponential. Okay, so with all that on board, all that stated, we can now give the computation, or the computational result. Conjectured by Nekrasov is that the full generating function, so the full generating function of these symmetrized symmetrized virtual structure sheaf, the associated DT invariants, is given as a statistic exponential of following. So, and here, I don't mean the, well, for the purposes of this talk, the precise thing in the statistic exponential isn't so important, really. The thing, the sort of thing to notice is it's a surprisingly simple thing. It's well, just the fact that it's a rational function is very striking. Okay, so this is the end of the 3D story, which took me longer than I anticipated, but that's fine. So, are there any questions on that? The classic 5-year-old story before we turn to the 4D cutting edge stuff. Okay, so suppose we now try and just naively, we want to do the same thing in 4 dimensions. Well, suppose we want to define something which is like DT invariants in 4 dimensions. So what happens if we just sit down and we're extremely optimistic, thinking we can just do this? So now, okay, so let's now redefine Mn to be Hilbert C4. So here we have, and we redefine our torus T to be, well, so T is now is still a 3-dimensional torus. So this is a slight difference from the 4D case. So here, this thing. So which 3-dimensional torus do we take? We have to ensure that we take the subtorus where the 4 coordinates, multiplied to 1. So in particular, like geometrically, we're saying that this torus has to preserve the volume form on C form. And so the geometric, so similarly to the 3D case, we have complete control over the fixed points. So the fixed points are they are solid partitions. So it's just the same thing in one dimension up, stacks of 4-dimensional boxes in the corner of a 4-dimensional room now. So these lie in this. Well, just certain subsets of Z4 positive integers. Okay, so what do we do? So we want, suppose we just wanted to have, we want to have an over Mn. We want to have a virtual structure sheaf in this case, and we actually want a symmetrized virtual structure sheaf, just to be even greedier. But we don't have a perfect obstruction theory anymore. Okay, so what is that? Why, or why is that? What do we have instead? Well, in this case, what do we have? We have the tangent space of Zmn equals still x1 OZ, and you can still write down, in some sense, the obstruction space is still x2 OZ, but then you also have the somehow the higher obstruction space x3 OZ, which you don't really know what to do with it. And technically speaking, it's just technically speaking, it's just a condition in the classical theory of defining these things via perfect obstruction theories, that whenever you write down this perfect obstruction theory, it has to have only 2 terms, and this has got 3 terms. So you can't really define virtual fundamental classes with this thing using the old technology. Another way of seeing that things somehow break is that the dimension of x1 minus the dimension of x2 in this case is not constant. So we can, in general, this will just jump around in as you vary set, and so it's not, you're not going to have a virtual dimension. So you have no virtual dimension defined, at least in the classical sense. But you can play some sort of numerological game to tell you that there might still be some hope. So what game is that? Well, you can see that dim x1 is equal to dim x3 by Z duality. And you can compute this alternating sum of these 3 X groups, and find that this will always equal 2n, and this is I guess Riemann-Roch, some Riemann-Roch computation, or however you want to compute it. I mean, there are different ways of showing that this is true. And what this means, putting these equations together, is you find that, well, dim x1 minus a half dim x2 is actually constant and is actually equal to n. Okay, so I'm not trying to create a convincing logical argument here, but somehow it's just saying that I'm saying if you, okay, supposing you could instead of taking x2 as your obstruction bundle, you could take like half of that as your obstruction, take some half-dimensional subspace as your to define your obstructions. You would actually have something which is invariant as you move z around. Okay, so this is it turns out one can make precise, and we will get to very soon to actually get something which is geometrically well defined. But I want to just jump right in and sort of give you the if you were sort of bold to just give you an extremely ad hoc definition of what you would be hoping for to compute in the end. So this is you might hope that when you compute the Euler characteristic of this symmetrized virtual tangent bundle, that you should be doing the following localization. You would be getting the following localization-like formula, where okay, so in the denominator you would get, let me write it like this. So something similar to what you had before, and in the numerator you would get this thing, and then I claim that, you know, that in sort of, since you're working with K-theory classes, the correct incarnation of this this ad hoc operation of taking like half the x2 space is you should take the square root of this thing. So here, and I should introduce the notation here. So when I say put a hat over something, it generally means it means I want to symmetrize it. So in this case, it's take the usual wedge bullet and tensor it with well, make it symmetric by tensoring by the inverse square root of the determinant. And right, and these are, I mean, here these are still polynomials in the TI, so it's a completely explicit thing. The main problem with this definition, so there are two. There's turns out there's an obvious problem with this definition. It is that even if you can take square roots of polynomials, and that somehow gives you a well-defined thing, but it's only defined up to a choice of sign. So in order for this to be an actual definition, I mean, this isn't really even a definition yet. So in order for it to be a definition, I need to tell you which square root you take, and there's always going to be two choices. So it's only up to defined up to a choice of sign at each fixed point. Okay. Well, the second thing to say is that actually this square root, I mean, so the square root, taking the square root of a polynomial is in general a pretty, I mean, that's only going to give you an algebraic function, but in this case, one sign that you're sort of heading in the right direction is that this thing is isomorphic to its dual as t representations. Again, this is a consequence of Serre duality. Which means that this thing is invariant. So thinking of it as a polynomial, it's invariant under ti goes to ti minus 1, right? So for an example, in the case n equals 1, this x2 is, so then there's a single fixed point, and we compute this thing to be and a further consequence of that is that the square root of so when you do the wedging operation and you take the square root, actually you will end up with a polynomial. So this is a polynomial in the ti, well, plus minus, but you might have to take the square roots of some of them. Anyway, so it's not like so this is if you spell out what this definition tells you to do, it's going to give you a rational function at each fixed point, but there's a sign ambiguity here. And with this, just using this ad hoc definition, we can state at least the main theorem, which is conjectured again by Nekrasov. So this is Nekrasov's conjecture is it's an ambiguous, it's a very ambiguous term. Conjectured by Nekrasov is again a formula for this for this generating function. Okay, so let me say for the correct choice of sign, and here I should, well, okay, let me just leave it like that for now. For the correct choice of signs, we have the generating function, the following. We can write down the following generating function. We take choices of sign. Okay, so we take over mn, and then we have to add in some further insertions and make this a slightly more complicated K-theory class. So if you write down this generating function, and I'll explain what the y and what the other ingredients are later, you again get an explicit formula for this as a pluralistic exponential, and again the what you're taking the pluralistic exponential of, as in the 3D case, is going to be a very simple thing. It's going to be a rational function. And it's not so important exactly which one, but let me just include it. Okay, so I haven't really told you, but y here is just a formal parameter, so it's just along for the ride. So I mean, much as you can think of it in the same way that Q here is it's essentially a formal parameter keeping track of keeping track of this n. You can think of this y as just keeping track of the various wedge powers here in ON. So this, if you write this out concretely, like the coefficients of this generating function. So the generating function, it knows about like the individual coefficients in this generating function are going to be basically it's going to be over Mn tensor sum which I on dual tensor. Oh, I should put a hat here. Super important. Okay, so these are the individual terms which are computed by this generating function. So it does, in particular, the kind of surprisingly perhaps. So it doesn't know about the generating function. Doesn't know the thing, the sort of simplest thing. Like this thing by itself is not one of the coefficients in this generating function. In some sense, well, this thing by itself is some kind of like, well, we'll see later. This is some kind of like slightly pathological object which you can define, but it's not really geometrically sensible. Whereas this thing, these objects are geometrically sensible. So what I'm hinting at, so when I say geometrically sensible, so far I've given you something very formal. I've just given you something to sort of compute and sum over all fixed points. And I should really make it clear, like I want to emphasize that really when I say choices, I mean in the end the goal here is just to see that this isn't really, we can replace this ad hoc definition with a proper definition. Like we can give this meaning by defining this thing, and then this formula becomes a theorem, and computing the sign becomes a computational problem. So it's really, we're not saying we should sit down and just make choices, but you're saying that really a computation. There's really a computation to be done here of which signs to put. But it's kind of, there's an interesting story here in that, like in working out this conjecture, part of the numerical evidence for the fact that this sum should have a nice formula was that well, you ended up with a nice answer for one specific choice of sign at each fixed point. And since there's an enormous number, well, there's a huge number of fixed points, and if you sort of are free to choose the sign at each one of them, and there's only one choice of sign which works, then that sort of that gives you a nice result that is somehow indicative of something, at least.
I think this discussion more reflects like a historical development of the subject rather than the logical thing. It's like saying,
for sure, yes, I should
like
emphasize
take the zeta function and flip the terms at random, you're gonna get like a bad function.
For sure, yeah. No, absolutely. I was sort of yeah. This is definitely, I'm definitely making a choice here to present it. I mean, I'm just for sure. 2 years from now, this is not how we would present it. But for now, like the I don't know. Yeah, we're not going to go around keeping this ad hoc definition. We now have a proper definition, and the sign ambiguity is really vanishes because we can define this properly. And you're right. I mean, there isn't a sign ambiguity. It's just historically the proper definition of this thing was missing. But anyway, this is the quick way to get to like to state the actual result. But yeah, okay. So what we want to, what do we really want to, what is the first point of order in order to sort of, in order to try and start understanding this, how to compute this thing? Well, the first thing to do is to understand what is this thing really? How do you define this? Okay, so this this gives so the answer to that is to look at a paper by Owen and Thomas from last year. So what they do mainly is they define a virtual fundamental class. So something living in homology, and they define a virtual structure sheaf for moduli spaces of sheaves on Calabi-Yau fourfolds. So right. So I should say, I mean, there's definitely like there's definitely some sort of intellectual prehistory to this. So it's at least at level of like defining the virtual fundamental class, this was, well, some of the results of Owen Thomas were, well, some of the construction. Sorry, this was previously. Well, there are previous constructions of virtual fundamental classes due to Boris of Joyce and Cao-Leung using different techniques and with different amounts of generality. So this is sort of previous work. So on Owen Thomas's work is really, I mean, it's got, for our purposes, it's got several, there's several sort of aspects of it which make it very suitable for working for our purposes. So first of all, they Owen Thomas, they work in algebraic geometry for one. So it's sort of directly adapted to our study of the Hilbert schemes, whereas Borisov and Joyce and Cao-Leung are, Borisov and Joyce are in sort of derived differential geometry, and Cao-Leung are in well, gauge theory, I guess. And both of these are sort of tools which are sort of technically something of a detour if you want to compute things in algebraic geometry. And sort of a main thing, logically speaking, is they define K-theoretic. I mean, they define well, K-theoretic invariants, which didn't really exist before, right? So the previous thing was only something in cohomology. Now we have, with their work, we have a definition in K-theory. They can also work on non-compact things. So they work on non-compact things, which I'm not entirely sure, it might have been sort of doable with the previous setups, but they work on non-compact things, and they also work T equivariantly. And crucially, we have a T localization formula. And in the end, we'll see this sort of ad hoc definition be, it's not an ad hoc definition, it turns out to be a computation. Okay, so Owen Thomas, their goal was to sort of do this for, say, compact, so to define this for sort of compact Calabi-Yau fourfolds, to define some structure on their modular spaces. The way they set this up technically is very, I mean, happens to work very well for us. So we only need a sort of a very small slice of what they do. So we only need standard model. I'm not sure if this is something me and Martijn have decided to call it, or if this is something Owen Thomas called it. So for moduli of sheaves on a CY4. So okay, so the standard model for moduli of sheaves on CY4 is meant to be the analog. Well, it's not meant to be, but it works as the analog for saying M. In the 3D case, M is a critical locus. So moduli sheaves on the Calabi-Yau threefold are critical loci. What are moduli sheaves on Calabi-Yau fourfolds? They are locally vanishing loci of isotropic sections of quadratic bundles. So that's a mouthful. Let me spell it out. So the standard model is to say you take your moduli space M and you embed it in some ambient space A, where A is smooth. You introduce a bundle. So Q some SOM bundle on A, where, okay, so we want to think of this as a vector bundle with a quadratic form. So let's specify that Q is the non-degenerate. So it has a non-degenerate quadratic form, and there's also an orientation involved, which is it's crucial. And then S is a section. S is a section of Q which is isotropic, in the sense that if you, which means that if you apply Q to S, you get the zero section. And finally, okay, so all this data, this package is what. So with this package, the local model is that M is cut out by S, right? So instead of being cut out by an exact one form, or instead of being a critical locus, M is cut out by this by a section, by an isotropic section of a quadratic bundle on something smooth. Okay, so given this, OT produce something living in K-theory. Okay, and there's some localization involved, but it's not too important. And here, I mean, they can only produce the symmetrized thing. The unsymmetrized thing doesn't actually exist. So I think I want to say one last thing before the clock runs out, which is the observation, which is sort of telling us that we can push this analogy from 3D case a bit further. So we're on the sort of right track with analogizing with the 3D case, which is that in the 3D case, it was globally a critical locus. In the 4D case, Hilbert C4 is globally given by a standard model. So we can globally find the setup above, where the Hilbert scheme sits inside something smooth. There is a quadratic bundle, isotropic section, cutting out the Hilbert scheme. This is extremely similar to, well, so it's very similar to what happened in the 3D case. Again, you embed it into the non-commutative Hilbert scheme of C4. Again, this is, well, let me just, so surjections here where onto modules which have dimension m. Okay, so we need to define a quadratic bundle living on the non-commutative Hilbert scheme. This is the following thing. I'm describing the fibers of the thing of this bundle. There's a natural quadratic form, completely explicit, you can write down, which is taking omega 1 so this thing is in, so the Fi here are in, and N, and this thing is then, I mean, so this thing lives in, well, so the whole, lots of elements off here, but anyway, the output of this is, you check, is actually a number in the end. And then you take the section there's a section of this quadratic bundle. Section of this quadratic bundle, which is given by, well, how do you evaluate this at a surjection n? Well, you take an explicit sum. So this gives you something in wedge 2C4. Where these, where I should have said, not Fi, I should have said. And the EI, so E1. E4 is the basis of C4. Okay, so so the point of writing down all this is just it's extremely concrete and simple to write down, and you check that this is an isotropic section, and you check that, well, when does this section actually vanish? That corresponds exactly to the condition that the operators xi and xj all commute, and so from this you really have described Hilb and scheme theoretically as cut out by an isotropic section of NC Hilb, and so you can apply the O. Thomas technology in sort of in a very direct and concrete way, in analogy to what happened in the 3D case, but that's well, to be continued, I guess. So that's, yeah, I should stop, I guess.
All right, questions?
Yes.
There were two things I was wondering. First of all, so you chose a 3-dimensional subtorus,
Yes.
At some point, I might have missed, why was that important, or why did you need to do that?
Let's see. So I'm not sure I can. Right. Let me. Okay. So I chose. So I took this three-dimensional subtorus, and what that means is that this whole setup. So C4 is a Calabi-Yau variety, and I want this torus. So it's a Calabi-Yau variety, meaning I can. There's an actual globally defined volume form, and I want T to preserve that volume form. So it's supposed to be, you want it to be T equivariantly Calabi-Yau. Now, as for exactly why you need it to be T equivariantly Calabi-Yau, I'm not sure I can point to the specific place where things break.
Well, for instance, that square root wouldn't be a square root. Won't be square root, right? That thing would not be.
Right. Okay. Yeah. For instance. Yeah. Exactly. So this claim here that x2 is isomorphic to its self-dual as a T representation, that uses serduality, but it uses serduality a form of serduality. Well, right. As Andre said, it would only be self-dual up to twisting by something different if you took the full torus. And I think more generally, this whole picture here, we want. So for this whole picture, we want T to act on everything in sight, and in particular, we want this quadratic form here to be T equivariant, which it wouldn't be if you let T scale this volume form. So that's another well motivation for why you need to stick to this subtorus. I mean, in some sense, to me, this kind of slightly surprising thing is that you don't need to stick to you don't need to be equivariantly Calabi-Yau in the 3D case. But yeah, anyway, that's those are two reasons.
All right, thank you. And the other thing I was wondering is, you said that in this case, the virtual structure sheaf doesn't exist. Yes. And one thing that I would maybe want to define the virtual structure sheaf as is take maybe like the derived scheme associated to the vanishing of this section, and then like take its structure sheaf and take like the image in K-theory of the non-derived thing and like take an Euler characteristic of these. Why is that not a good definition of the virtual structure sheaf?
Well, I think let me just so doing that, you would have defined something. So what you're describing is, so you can always, if you have a scheme which sits inside a smooth ambient space and it's cut out by a section, you can always use that to define a virtual structure sheaf, to just write down the Kosovo resolution as we did in the 3D case. But my claim is that if you're doing that, you're not. I mean, you're going to. Well, I mean, it's certainly a fact that you're going to get the wrong thing. But
I mean, that thing will have a wrong virtual dimension to begin with.
That's the first. Yes, that's the first point. I mean, you would end up with something in the wrong virtual dimension. So really, I mean, there's a when we get to explain what. Yeah, sorry.
Maybe I can try to answer Davis's question. So suppose you have a bundle which has weight like W plus 1 over W, and then so that's a self-dual bundle, and you'd like to define something that's cut out by an isotropic section, which could have a weight W or have weight 1 over W. So you don't know if you just take the structure sheaf, that will be either 1 minus W or 1 minus 1 over W. You don't know which is which, so you don't know ahead of time which is the choice. However, you take the symmetrized version, that only differs up to a sign, and the sign you can fix. So if you take the symmetrized version, the only difference is the sign, and the sign you can fix if you have some orientation. So that's why this is why this isotropic stuff only exists if you symmetrize it, and if you don't symmetrize it, you can't really define it.
Right. So there are sort of two things. There are sort of two things one can wonder is why. Right. Why can't you? Okay. So one thing is you can't define the virtual structure sheaf just by taking the naive. Well, it's not the naive, but just by taking the Quadratic resolution, because that would essentially mean your virtual structure sheaf comes out of a two-term perfect obstruction theory, which is what we had in the 3D case. And this is just what we're defining here. It's just something different, right? It doesn't come from that. And in particular, like it's, the Owen Thomas are trying to prove a result saying, from the data in this three-term obstruction theory, you should be able to extract a class. And the way to do this is not to take the standard model and take the Quadratic resolution. That just gives the wrong thing. And then we haven't really seen what the definition of this virtual structure sheaf is in this 4D case. But once you write down what that is, as Andre said, it's sort of one can see that there isn't. Yeah, I think maybe this will be clear when we actually define this thing, that you can't really hope to have something which isn't symmetrized. In order for it to be well defined independent of choices, you have to symmetrize.
Okay, thank you.
Sure, more questions.
I have not a question, but rather a historic comment regarding this choice of signs, because in localization formula for unitary cobordism theory, the sum of over fixed points come with a choice of sign. And this choice it's not a choice, with some signs. And these signs are, because unitary cobordism is a theory of quasi-complex manifolds. So if it's complex manifold, then the signs are always positive, it's just ones. And the difference in signs comes from orientation of stable complex structure with what you have locally. Probably it's absolutely irrelevant. Just your discussion about the choice of signs just remind me an old story. It was discussed relatively recently in details in paper by Ries and Buchstaberitz about 5 years ago.
Mm-hmm.
I don't know if it's useful, but probably.
No, but thanks. Yeah. I don't know either, but it's.
No, actually, you see, you're writing a sum over fixed point. It turns out that contribution from the localization formula requires a proper choice of a sign in front of for each of fixed points.
Mm-hmm. Mm-hmm.
And if you have equivariant theory of a complex manifold, the choice is fixed as once for all points. If you're dealing with a quasi-complex manifold, then they might be different.
Mm-hmm.
I'm sure it's related, because you can also define this this class as being cut out by a section which is not exactly holomorphic.
Probably.
Like Nekrasov likes to define it. You take equation where you take a you take maybe instead of saying x1 and x2 commute, you say that the commutator of x1 is the remission conjugate of the commutator of x3 and this sort of thing. So it's not exactly a holomorphic thing, but I think the difference from this being holomorphic, I think it's got to be related to the sign you're talking about.
Mm-hmm.
In my guess. More questions? Well, if there's no more questions, let's clap our hands in gratitude to Jørgen, and we'll be looking forward to his talk next week. So thanks, Jørgen. That was great. Thanks.
Thanks.
Oh yeah, don't forget to send me the notes.
Okay, sure.
So, yeah.
Will do. Yeah.
Thanks again.
Okay. Yeah. See you in a week.